Okay, so today we're going to change our viewpoint of geometry a little bit, and instead of talking about reconfiguration problems and motion planning, we're going to talk about representing graphs with geometry. Now, I'm going to give a couple of examples of this. So in previous talks, we've looked at reconfiguration problems for chains of links. Then we took a look at another type of problem in robotics that has some interesting geometry for us, namely localizing a robot, how a point robot figures out where it is, and then how it navigates around the environment. And the point of the last talk was kind of to illustrate the difference between, thank you, what it looks like to take a computational geometry, pure computational geometry point of view, and then what happens when you move over to a related field, like your colleagues in robotics or artificial intelligence, and they like to do simulations and experiments. And finally, moving all the way over to the experimentalist, you get some new yet other kinds of problems when you study motion planning for robotics. But today we're going to take a different point of view. We're not going to talk about motion. We're going to talk about graphs. So we're going to think of graphs, after all, as just representing binary relations. And we're going to consider that those binary relations could be binary relations between some kind of geometric objects. So we could have objects floating in space, and we could ask whether they intersect. We could ask whether they see each other in some direction of sight. We're all familiar with interval graphs, intersection graphs of intervals on the line, and so forth. So in many ways, we can use geometry to express the binary relationships in a given combinatorial graph. So we're going to take a look at just a couple of examples of this today. One of them, we're going to start with a visibility representation of graphs, and then depending on our time, we're going to take a look at representing graphs as objects that touch. So the context here is graph drawing, and I believe you had a talk in your workshops before this school began on graph drawing. Is that right? I think so, yeah. So you should all be aware that there is something out there called graph drawing and network visualization. They've had roughly 25 annual international symposiums on this topic now. It started off being called graph drawing, but recently the name has changed to graph drawing and network visualization, because graph drawing maybe sounds like something artistic, and it's not exactly that. So there's a conference out there. The next one is in September in Athens. Basically, what that community of people has been doing, and it's a very enjoyable community because it embraces people who are working on very theoretical, discrete geometry problems with no interest in applications, all the way to people who are designing software, implementing it, doing experiments, starting companies, hiring students in computational geometry to work in the companies, selling software. They have demos at these conferences, contests, and people respect that whole theory to applications spectrum, which is one of the amusing things, appealing things about this group. So originally, the idea, the motivation behind drawing graphs nicely, where nice means a couple of things. And watch out, because the graph drawing books talk about, and papers, they talk about aesthetics. And usually aesthetics means something that's beautiful. And mind you, this community can create some really ugly pictures of graphs. If they're interested in finding a minimum area layout with at most 5 bins per edge or something like this, putting some constraints on what it is you're trying to optimize can create some really ugly drawings when you try implementing the algorithm. So aesthetic definitely doesn't mean beautiful. It means good according to some criterion that someone has specified. So for example, it usually means that layout is nice if it's suitable for laying something out as a network. Laying out a circuit, you don't want the edges to cross. You want the angular resolution between edges to be large, or the electrical properties of the circuit change, and so forth. So you have some properties like that, and you want a drawing that respects those constraints. And then you say you have an aesthetic drawing. Well, it just means one that's useful for your purposes. Another type of motivation that the community also looks like is coming from information visualization. So you want a graph that's easy to read and understand. And also, typically you want a graph where you can perform some task on it efficiently. So actually there are people in this community who do user studies. They'll give a user several pictures of the same graph and ask them to perform some task on it, like determine if vertex A is connected to vertex B. And you have some big complicated diagram, and your eye has got to trace around all the edges and figure that out. And you measure the number of seconds it takes the person to press the button and say yes or no. So you start doing user studies like people in social science do. So there are some people who do that kind of study as well. So information visualization, that's also an area of interest. Now, in this context, one can think in the graph drawing context, we can think of the fact, for example, that planar graphs can always be drawn with edges that are straight. Wagner's theorem. Take a planar graph. There's a way to draw it in the plane so that the edges are straight line segments and they don't cross. Would be considered a graph drawing result these days. The aesthetics is having straight lines for some reason, and so that can be considered graph drawing. Planarity testing. We have algorithms for testing whether a graph is planar or not. So that's kind of, can you draw the graph in a particular way so that the drawing has some particular property? That's a graph drawing result. And I already told you about the graph drawing symposium. Okay, so let's start talking about visibility representation. So just as the first two talks weren't classical, pure computational geometry, this is not going to be pure graph drawing either, because it's not working directly with laying a graph out. It's exploring what happens when we use the expressive power of geometric relationships to describe a graph. So here we go, bar visibility graphs. So one thing that was looked at early on in visibility studies is this. You have a collection of horizontal bars in the plane, horizontal line segments, and you use them to represent your vertices. And then you want to know if you can represent the edges as vertical lines of sight. That's a bar visibility graph. So there's some results about that I'll just mention. But what we wanted to do, some work I've been involved in, is generalize bar visibility results to 3D. So instead of having line segments, what about stretching the line segments out and having rectangles that are floating in 3D space, and look at the visibilities amongst them? And then also, what about generalizing bar visibilities in the plane, stay in the plane, but instead of talking about visibilities of bars, talk about visibilities of rectangles in the plane. So those are two kind of natural generalizations that I'd like to talk about. Okay, so here's the illustration for bar visibility. You have a graph there on the left, and then we're representing it with segments, and those dotted lines are visibilities between the segments. Now, in this model of visibility, if you start to think about the problem for a little, you discover you have got to figure out whether it counts as to say two segments are visible if they see each other along a line of sight that passes through their endpoints. And the answer is no, we don't allow that. It's a standard model of visibility says that things have to be visible along something you can fatten up, so that if you're looking at a if you're looking at a line of visibility, you can actually fatten this up to create a rectangle of arbitrarily small but positive width. You need a rectangle of visibility between two line segments. So one easy observation that we were noticing in the work group last time we met is that a bar visibility graph has got to be planar. It has to be planar because you can take the bars and fatten them up to make rectangles and then pick a representative point inside each rectangle and take a visibility, vertical visibility between the bars and just join the representative point over to the base of that vertical visibility. And when you do that, internally, you won't have any edges crossing one another. You'll just have this vertex looking radially around its boundary. And you certainly won't have vertical lines crossing one another because they're parallel. So you can see immediately that if you can represent a graph as a bar visibility graph, it has to be planar. So there's a couple of representations you can think about here. One is called strong, which means that if you have the representation, the rectangles, the bars, looking at the bars, can you reconstruct what the original graph was? Well, certainly you can determine the visibilities amongst the bars, but there might be more edges than you originally had in your graph. So we say a representation is strong if there's an edge of visibility between two bars if and only if the graph had that edge. Otherwise, you say it's a weak representation. If when you construct all the visibilities amongst the bars, if it's a superset of the edges of the original graph, we say it's a weak representation. And Steve Wismath and Roberto Tomasia and Yanni Tolis proved that a graph has a weak representation if and only if it's planar. So all planar graphs can be represented this way. And if you want a strong representation, then you have to have all the cut vertices of your graph on a common face, let's say the outside face. So just some related problems. I mean, this is just nice questions to ask in geometry, but areas where you might be interested in this kind is, for example, in motion planning problems, we're very interested in things that see each other. And maybe Ali, when he talked about motion planning algorithms in your pre-workshop workshop, might have talked about the idea of moving a point around in a polygonal environment and using visibility edges to help plan a path from a start vertex to a finishing vertex. So visibilities amongst polygons is certainly something that's interesting in that context. Art gallery problems, you know, have a lot of visibility problems. A famous, well, in my mind it's famous because it still hasn't been solved, is a problem that was asked by one of our graduate students at McGill back in 1983. It's a beautiful problem. He says, if I give you the cyclic ordering of the vertices around some desired polygon, and I tell you what vertices I want to be visible, can you find a way to do it with a polygon? Can you find a polygon with that cyclic ordering of vertices around the boundary having exactly those desired visibilities? And we still don't know the answer to that. It's decidable. You can formulate this in terms of Tarski sentences and say it's a decidable problem, but we know some special cases, but the problem is still open. Yeah. And I already mentioned graph drawing. So here, I'm going to mention some results that came out of a workshop, one of the famous Bel Air's workshops back many years ago. And it has some names you'll recognize, like Jit Bose. He was one of the speakers a couple of years ago. And let's see, who else? Tom Shermer. We were talking about Tom Shermer the other day in the problem session. He has an NP completeness proof that we were talking about. Mark van Creveld, he's one of the the authors of the standard 3 marks plus Otfried book. So we were talking about some of these ways of generalizing the result about bar visibility. They said, okay, let's go to 3D. Let's generalize to 3D. So bars are going to be pulled out into rectangles of some shape, floating in parallel. And vertices are going to be represented by lines of sight. And we call these rectangles in parallel visibility. We wanted to know what graphs can they represent. As moving to the third dimension adds some more power. So the first thing you notice is, well, now you can represent some graphs that aren't planar. For example, you could have a bunch of rectangles this way, and above them a bunch of rectangles this way, and you've just represented an arbitrary bipartite KMN, just that way. We check that you can still represent all planar graphs. You don't hurt yourself by moving to rectangles. You can pull the bar representation out into 3D. And now, when you look at squares, if you say, what visibilities can you represent amongst squares? Let's say, unit squares. So squares can have different sizes after all. Let's say unit squares. There's a unit. Then it turns out you can represent K7 with unit squares floating over one another. And it's a really fun puzzle to figure out how to do that. But you can't do K8. And now the proof that you can't do K8 was done by computer search. And it wasn't a straightforward computer search. It was not a straightforward computer search. So if anybody sees a nice proof that you can't represent K8 as unit squares floating in 3D, then please let me know. It seems it's not an easy problem as far as I can tell. Now, okay, if the floating axis-aligned rectangles must be unit disks, then Kn has a representation for every n. You're supposed to laugh. There's something funny there. If the axis-aligned rectangles are unit disks, it's a joke. Suppose the objects that you're floating in 3D aren't rectangles. Suppose they're unit disks. Right? They're unit disks. Can you represent every Kn? And the answer is yes. You can take your unit disk and just move it around in a spiral way, in such a way that every pair of disks sees each other. If these axis-aligned rectangles are arbitrary rectangles, so you don't insist that they have to have the same. They don't have to be squares. They don't have to be the same rectangle. Any rectangles at all are fine. Then you can represent Kn at least 22, but not any greater than 56. You can't represent more than K56 that way, but you can do at least K22. So there's a gap here that's been open for quite a while, and if anybody wants to explore the challenge of programming this in a clever way and seeing what they can get, be most welcome. And here's somebody else you recognize, Gunter Rota. He's been a speaker here. So he had one of his students program this, and we had figured out 21 by hand, but these guys came up with 22 with a computer search. And they let their program run a long time, and they didn't get 23, but that's not proof. If the convex polygons have a bounded number of sides, then you can't represent all graphs. You can represent every graph with floating convex polygons, but the number of sides you need in your convex polygon grows as the number of vertices grows. Look, there's somebody else you recognize. Helmut Alt was a speaker here a couple of years ago. So we claimed that it's NP hard to determine whether a graph can be represented by rectangles of the same size and shape. But in fact, when we went to write up the journal version of this paper, we started seeing details that had eluded us. And so I'm saying here, we claim that it's very slippery proof. It's easy to make a mistake with geometry, as you know. So I'm not really sure that we know that. So let's go back to the plane. There's an exploration of 3D there, but let's go back to the plane and see how we can generalize bar visibility in the plane to rectangle visibility. So now instead of bars, we're going to have rectangles, just like our work group has been looking at. And we're going to allow rectangles to see each other vertically or horizontally. So here's a set of rectangles. They generate a visibility graph. I'm supposed to go the other way and say, let's take an arbitrary, notice, by the way, these visibility lines can cross. So it's nothing that says this has to be a planar graph. So if we start with the graph, can we find a set of rectangles that realizes exactly those edges? And there, the answer is, by Tom Schermer, that's an NP-complete problem to determine whether a graph can be represented by axis-aligned rectangles if you're allowed to look horizontally and vertically. Well, why is the recognition problem hard? And Ilyana Strinu and I had some thoughts that one reason that it's hard intuitively is that there's so many choices to be made when you try to design the rectangles. For example, look how much information is missing here. If you have a real set of rectangles, then you know the directions of their visibility. So B looks up to A. So you have a directed edge, and not only do you have a directed edge, but you also have a direction associated with it, whereas back in this graph, B could have looked east, west, north, south. We don't know. So that information is missing. That's one kind of information that's missing, the direction and the nature of the visibility. Another thing that's missing is the possibility of multiple edges. So here, topologically, C sees A on both sides of B. And there's nothing in the original graph that shows multiple edges. So that's another thing that's missing. If you're trying to create the rectangles, this would be very helpful to know whether that type of relationship was expected. Another thing that's missing, and just giving a combinatorial graph, is the cyclic order of the visibilities around the point, or around the point that's representing the rectangle. So if I have a little bug here on B, and it walks clockwise around B, then first it's going to see this upward edge of visibility, then the eastward it's going to look to D, and then down to C, and then it's going to keep walking around. It's not going to see anything new. So that information of the ordering of those edges, that's also missing. So we're missing a huge amount of information. Oh, another thing we're missing is which rectangles can see the sky and the ocean and see infinitely far in both directions. We don't have that. So basically, we're not being told much at all. So that seemed like something to play with. What if we give more information in the original graph before we ask the question, can you realize it with rectangles? So one thing we did was to add a frame around, or notice, let's say we just have a collection of rectangles. Notice that we can add a frame around it, just make a box around it of rectangles. And now that's a way I can capture the information of which rectangles can see arbitrarily far. They'll see north. They'll see A sees south. So A has a way of seeing arbitrarily in the southern direction if it sees this rectangle S. So that's a way to capture that. So we came up with a new notion of visibility graph. Instead of just the original structure, what we're going to do is frame the set. Imagine the set of realizing rectangles has been framed. And we're going to define a graph that captures the vertical visibilities that we'd like to have. And we're going to define another graph, note D for directed. So it's going to be a directed planar graph that captures vertical visibilities, and another graph which captures the horizontal visibility information. Notice these two graphs are going to be on the same vertex set, except that the vertical visibility has got two vertices that the horizontal doesn't have, and vice versa, namely these two frame rectangles. So with that exception, the other vertices will be the same vertices, same collection of boxes. So here's a picture of the vertical visibility graph, DV, for if we have the set of rectangles. Here's how we would define the vertical visibility graph. So as you can see, I just have some lines of sight. I picked a reference point here, nice planar graph. And you notice that it's directed upward, it's acyclic, it has some nice properties. In particular, it's what's called an ST graph in graph drawing terminology. What's an ST graph? Well, it's a planar directed acyclic graph. Easy to see here by the argument we mentioned earlier. It's a planar graph. It's embedded, so we know what the faces are of this graph. It's not only planar, but we're talking about a particular embedding. It's two connected. The underlying graph is two connected. Why is it two connected? Well, if I take any pair of vertices, I can always just keep walking upward until I get to the top. And I can also walk downward with visibilities. B can go to C to S. So any pair of vertices has a path to the top and has a path to the bottom. So there's a cycle containing any pair of vertices. Mind you, the cycle might close before you got all the way to the top or the bottom, but there's the cycle. So it's two connected. It's got a single source coming from the ocean rectangle, single sink coming from the sky rectangle. And the source and the sink are on the outside face of the graph. So that's the definition of an ST graph. And in particular, it's showing this directed vertical visibility graph is going to be an ST graph. So ST graphs have got some nice properties, which we're going to use. Here's the same thing for the horizontal visibility graph. We have these extra rectangles on the east and west, and now we're looking at horizontal visibility. So we get a directed ST digraph from a set of rectangles in the plane. Okay, so what's a topological rectangle visibility graph? It's that structure that you get from an actual set of rectangles. Rectangles, a real set of rectangles would give rise to this. These two directed acyclic graphs, ST digraphs, on the same set of vertices except for those two special pairs. That's what you get. So we defined a pseudo-topological rectangle visibility graph. It's kind of a mouthful, a pseudo-TRVG. And it's a combinatorial object, namely it's this pair of ST digraphs with all the properties of what you'd get if you started with a set of rectangles, except that we don't know we started with a set of rectangles. It just has the right combinatorial properties. And the question is there some way of realizing all this combinatorial topological information with some rectangles? So here's a new problem. Given the dv and the dh, is there a real set of rectangles such that when you construct the visibilities of that set of rectangles, you get what you hoped for as input at the beginning? So that's the TRVG recognition problem. Can you find the rectangles? So I'll just tell you what the results are, because the necessary and sufficient condition is going to take a little bit of work to get to. So we found a way of characterizing these pseudo topological rectangle visibility graphs. We can test these things to determine whether or not there is a set of rectangles that constructs the properties we want. And in fact, if the combinatorial information passes the test, which you're going to give in a minute, then we have a construction. And the interesting thing about the construction is it gives them, if you insist that the vertices and edges have to go at integer positions, the coordinates of the boxes have to be integer coordinates, then the set of rectangles we're going to get is going to have the minimum possible width and, at the same time, the minimum possible height amongst all possible realizations of that information. So that sounds pretty cool, because you could have an application like this. Somebody gives you a set of rectangles, and they say, can you please reconstruct this set of rectangles for me so that I have exactly the same combinatorial topological properties, but I want the minimum area, I want the smallest width of the picture and the smallest height of the picture, with the minimum possible bounding box. Can you do that, please? Answer, yes, we can. Now, that's kind of interesting. But there's a caveat here, and that is this is subject to your wanting to have a set of rectangles that exactly has all that information that's given. So you might be perfectly happy with just the visibilities and you don't really care about the cyclic ordering of the visibilities around the boxes. Then this result isn't going to help you. This is just saying if you really want to capture exactly all those properties we're giving in the input, then you can't do better than our construction. It gives simultaneously minimizes the width and the height. And there's been algorithms in VLSI that do things like take a bunch of boxes and minimize the width, and then they try to take that and work on the height, and they go back and forth between fixing the width and fixing the height. But this is simultaneously optimizing both. It's just that you have to really want all those properties. Okay, so in order to state the characterization, we need a little bit of background. So we need a notation for the dual. So it's a planar embedded graph, so it has a dual. So we're going to denote the dual of our vertical ST digraph by a star, and similarly DH is going to be DH star. And now here's an easy trap to fall into if you're relaxing in a comfortable chair in a dark auditorium. That is, the dual of dV is not dH. Very sorry, it is not. The dual of the vertical visibility graph is not equal to dH, and the dual of the horizontal visibility graph, it's not. The notation is beguiling, perhaps, but it just doesn't work. So, okay, so really what we have are 4 ST digraphs to play with. The original ones, the directed horizontal visibilities, vertical visibilities, and their duals. And it turns out one nice fact about ST digraphs is that their duals are also ST digraphs. So we have 4 ST digraphs going on. And what we have to do is weave together their properties to come up with a characterization of when we can realize them as rectangles. So here's a little bit more background information. In any ST graph, the incoming vertices and the incoming edges and the outgoing edges are separated from one another. As you go around this vertex, you see all the incoming edges, and then you see all the outgoing edges. They're separated. And at that separation between incoming and outgoing on the right, you speak of that as the right face of that vertex. And similarly, we have the left face of the vertex. That's a fact about ST digraphs. Here's some more notation. Sorry about the notation, but without the notation, I can't state the characterization. Let's say we're looking at the dual of the vertical visibility graph. So here's a vertex representing some rectangle. Here's the incoming visibility edges, the outgoing visibility edges looking vertically upward. And now I'm going to have faces there in between these edges, and I need some notation for them. So this face here is going to be, so that's the left face in the vertical visibility graph of U. Remember, we just defined left and right. I'm going to use the same notation for that point. So in the dual graph, I'm going to use the notation, just recycle the notation and say that's vertex LV star of U. And I'm going to, just as a convention, direct the arcs of the vertical visibility dual from left to right across the arcs going into U. And there, this arrow should point the other way. Okay, so characterization. Now we can get at the characterization, weaving these four graphs together. So you can realize a pair of these ST graphs as long as you satisfy both these conditions. So I'm about to fill in the blanks here, about to show you the conditions that have to be satisfied. So the first one is going to say, for each pair of vertices in the vertical visibility graph, some property has to hold. And likewise, for each pair in the horizontal graph, some property has to hold. Okay, let's see what are those properties. So here are the properties, and I'm going to show you a little intuition for this after we state the property. So this says if there is a path, a directed path from U to V in the vertical visibility graph, then you have to have a directed path from the left face of U in the dual to the right face of V in the dual and the horizontal graph, and the horizontal visibility graph. So I'm going to show you a picture in a minute why that's true. If you can travel from the visibilities from U to V in the vertical direction, then if you look at the dual of the horizontal visibilities, you have to be able to travel from the left face of U to the right face of V in the dual. Okay, and so what's the other condition going to say? Well, something entirely analogous. If you can go from U to V in the horizontal visibility graph, then you have to be able to go from the right face of U to the left face of V in the dual of the vertical visibility graph. So it's relating properties of the horizontal graph to the dual of the vertical graph. And we'll see where that comes from. Here's the intuition. So here's a picture of a horizontal visibility graph in an actual set of rectangles. So there's a path of vertical visibilities here from C to A, these little pale green edges there. And we're going to use the vertical visibility segments. You notice that they're crossing horizontal lines of sight. And so as we travel along these vertical visibilities, we're moving from one face to another face in the dual of that horizontal visibility graph. And by the way, what's this black spot here? It's just a vertex that's representing this rectangle in the dual of the horizontal visibility graph. Okay, and so I can make a little path across these horizontal lines. What do I do when I get to the box? Well, I can just my path can walk around this box. I need to travel from this face to this face, or I could just regard it as, I might cross several, if there's several visibility lines, I might cross several faces to get to the top of the box. I can do that. Just walk around the box, and I'll get a path through the dual of the horizontal visibility graph. So there's our little path that we're taking. Okay, so what's the construction? So that's the intuition, where those conditions come from. Just imagine how the visibility lines are walking across the faces of the visibilities in the other direction. So here's how to compute the corners of the rectangles that are going to realize this graph. if the test is passed. Those two combinations, each pair, remember, in each pair, and the horizontal and vertical visibility graphs had to satisfy that test. So let's say we've tested it. It doesn't take much time to test. How do we compute what the rectangles are if the test is passed? A rectangle U is just going to have coordinates given by this. So what is this? We're going to assign 0 to the source node in each of the two dual graphs. And then all the other nodes in each of these dual graphs, we're going to number by the length of the longest path that goes from the source to that vertex. So we're numbering by longest paths. And intuitively, that's because you have to make your box big enough to accommodate all the incoming visibilities to it. And incoming visibilities mean that in the other direction, you're crossing lots of faces. So crossing lots of faces means you need to have a wide box or a tall box. So this numbering works. You take the numbering that you get there by this longest paths, and you make the lower left corner of your box, for example, have coordinates, the number that you assigned to the vertex in the dual visibility graph that corresponds to the left face of U, and so forth. Same with the other corners. And that works. I'm not going to give you the proof, but I'm just going to tell you that it works. So that's the construction. And it suggests a couple of problems. Can you generalize this to 3 dimensions? Let's say you have shoe boxes in 3 dimensions, and they get to look up and down in 2 directions in a plane, east, west, north, south. Can you use the same techniques? Well, absolutely not, because as we already noticed, if you have 2 rectangles floating in 3D, then if you have rectangles floating in 3D created, say, by the bottoms of all these boxes you're interested in creating, you can represent large, complete graphs. So certainly, you're not going to have planar graphs anymore. So we've been heavily using the properties of ST digraphs, but if we move to 3D, we're not going to be able to do that because we can represent large Ks, K7, for example, if the shoe boxes have squares on the top, and we had that gap, K22 to K, I forgot, 60, I don't remember, 56. If we have arbitrary rectangles, axis to line floating in parallel. So the same techniques are not going to work. So what can you say about visibilities amongst objects in 3D, axis line? All right, so let's see, we have a little bit of time. I'm going to talk next about a different kind of geometric representation, namely contact representations of things. And by contact or touching realizations, I mean things that don't intersect, they just touch on their boundaries. So the closed objects intersect, but not the open objects. So if you like, you can think of this as visibility graphs with extremely limited visibility. You have a visibility edge, and it has length 0. You're touching that object that you can see. You've got to be really, really up close to touch and see the other object. So here's the context, proximity graphs. So we're familiar in computational geometry. We might have a point set, and we want to ask questions like which pairs of, what's the closest pair of points? And they're proximity graphs, a number of proximity graphs that have this kind of flavor. One thing you can do is put an edge, one kind of proximity graphs is put an edge between 2 vertices, provided, let me just say right before I forget, we're going to work with, there's a polygon, connected. G is connected. Going to work with connected graphs, because what I'm going to say isn't true if you have a lot of different connected components. So you can think of it as facts about the connected components, if you like. All right, so we have a connected graph, and it's created this way. You take your point set, and you put an edge between two points, if and only if those 2 points are each other's closest neighbors. So A is the closest neighbor of B, and B is the closest neighbor of A. So what that means geometrically is that the figure 8 that they generate is going to be empty. So here's say point A. There's a point that's its closest neighbor, so I have a disk around there. That disk is empty of other points. And now likewise for B, if A is the closest neighbor of B, I put a disk around B, that's also empty of other points. So this figure 8 shape is empty of other points, except, of course, for the 2 starting points. So that's these figure 8s, empty figure 8s, that's generating what we call a mutual nearest neighbor graph. The 2 neighbors are got to agree. I'm your nearest neighbor, and you agree I'm your nearest neighbor. So this gives rise to a recognition problem. You have a connected graph. Is there a point set that has this given input graph as its mutual nearest neighborhood graph? So the first thing you notice is that all the edges have got to have the same length. If A is the closest neighbor of B, let's call that length 1, and if B had an edge to C, well, that's ridiculous. C has got to have the same distance. If it's going to be a closest neighbor to A, to B, it has to have the same distance that A does, or it's not a closest neighbor. A would be the closest neighbor, but not C if the length of C were greater. So all the edges in this graph have the same length. And let's just say that's the unit length. Another observation is, what about the non-edges? Well, if I have a point here that's not connected, well, okay, here's points. They're lying outside this figure 8. But if I had a point inside the figure 8, then that would contradict that this A is the nearest neighbor of B. So if B and C are not adjacent, that means C has got to lie outside. It's got to have a distance greater than 1 in order not to be a nearest neighbor of B and not contradict the other nearest neighbor. So no non-edge has length less than unit length. So notice these mutual nearest neighbor graphs are exactly these things we call coin graphs. So coin graphs is, you take, what's your favorite denomination? I don't know, pennies. Do you have discs and coin discs and around? No, you have paper for small denominations. I don't know. Maybe you have some coins, all the same coin, all the same denomination, discs, say, and you let those represent vertices, and you put them in the plane, and where they touch, you can put an edge. So that's a coin graph. So when you do that, then the figure 8 created by those 2 touching coins, that's empty of other coins. We're not going to allow the coins to overlap one another. So a mutual nearest neighbor graph, same thing as coin graphs. And of course you can define this in any dimension, mutual nearest neighbors in any dimension, but there your coins are going to have to grow with the dimension as well. So in 2D, it was shown that the recognition problem is NP hard. And we claimed that somewhere in our paper that, oh, well, extending to 3D it's obvious how to do that. You just put a couple of layers, sandwich your graph in between a couple of layers in 3D, and you have the same construction that's going to work. Well, if you try to write down the details of that, it turns out lots of things go wrong. It's not so easy to show it in 3D at all. And I had a master's student who was able to show that in 3D, the recognition problem for touching unit spheres is indeed an NP-hard problem. And for arbitrary dimensions, it gets more complicated. It gets very complicated. So it's open and arbitrary dimensions. So let's just take a look at the 3D, what happens in 3D. So here's a mutual nearest neighbor graph in 3D. So here I have 3 vertices, A, B, C. They form an equilateral triangle. Okay. And now I want to introduce a 4th point that I want to be equidistant, distance 1, away from each of those 3. I have no choice to make a pyramid, a tetrahedron. But notice this 4th point could go up here or it could go down there. So I just have 2 ways that I could realize this K4 as a 3D mutual nearest neighbor graph, deciding on which orientation I try to use. So here's ABC going around the base, and here's ABC going the other way around the base. It's just a mirror image. I have 2 ways of realizing that K4. There's no way to add a 5th point to that picture. Where would it go? Well, the 5th point would likewise have to be unit distance from ABC, so it would have to be the other point down here, but then it would be too far away from Z, so you can't do it. K4 is the biggest clique you can realize in 3D with mutual nearest neighbor graphs. All right, so here's another example. By the way, I'm showing you these for a reason because we're going to use them in this construction I'll sketch. Here's another 3D mutual nearest neighbor graph. It's combinatorially, it's a wheel. Here's the hub, and here's the vertices around the cycle with another vertex that's adjacent to everything around the cycle. So kind of 2 wheels that agree on the cycle. And now, what do we know about that? Well, we can have A, B, C, D as the cycle. And now we can put 1 vertex at the top, a pyramid, and we can put another vertex in the mirror image position, and we'll get a realization of this combinatorial graph is a regular octahedron. And that's you have to do it that way. That's the only realization. So now I claim, and this takes more effort to see, but it's not too hard to see, that these objects are mutual nearest neighbor graphs, and you don't have much choice for how to draw them. So what happens here is that the blue vertices lie in the plane, and the green vertices, they start off in the plane, and then I just take the green vertices and start lifting them up until I get equilateral tetrahedra here over those faces. So this is the mutual nearest neighbor graph. And now on the right, and you can look inside here and see you get an octahedron, namely this green thing, this blue thing, and the edges that connect them. This is an octahedron in here. And this octahedron has got tetrahedra glued to some of its faces. So this face here has a tetrahedron glued to it, tetrahedron glued to the faces. So it's a octahedron. One way to think of it is it's an octahedron with tetrahedra glued onto 3 faces. Now what's happening on the right is that's this same picture, but in a smaller scale. And now I'm just kind of continuing this lattice of blue a little bit. So I've added on a strip of 3 more triangles down here in the base plane. And I've added on another green triangle in the plane that's the appropriate height up. And this object is an interesting object. So the underlying graphs have got 2 mutual nearest neighbor graph realizations as touching graphs of unit spheres in 3D, and the 2 ways come from the mirror images of one another. So these 2 graphs, just 2 ways to realize them in 3D. Now it turns out that this structure of having an octahedron with a tetrahedron glued onto it was something that was noticed and investigated by Alexander Graham Bell. So Alexander Graham Bell was Canadian, or at least lived in Canada, actually. Maybe he was Scottish and moved to Canada. I don't know. He was a wealthy guy. He had a research outfit. He had a mansion, stone house back early 1900, and he was doing research in mathematical investigations and interested in communication and telephone and all that. He's the person we named the telephone company after in North America for a long time. So he called this the Octet Truss, and I'll tell you in a minute why I was interested in this. And it turned out this same structure was rediscovered 50 years later by Buckminster Fuller. Oh, we're talking about architectural geometry, aren't we? So Buckminster Fuller, the person who's interested in geodesic domes and so forth. So he patented it, not realizing that Alexander Graham Bell had discovered this many decades earlier, and he called it the Octet Truss. So why was Alexander Graham Bell interested in the Octet Truss? Well, this is a figure taken from National Geographic magazine, and it was kind of a scientific magazine of the day, and the picture was taken in 1902. So Alexander Graham Bell was interested in flying, designing flying machines. He thought he'd start by trying to design kites that were very light, but were very strong enough to hold a graduate student. So that's a joke. Here's a graduate student. Graduate student's got to take off in the kite. So let's make sure that this is a nice, safe, strong kite. That's my fantasy that is a graduate student. I don't really know. Anyway, so these are illustrations from the National Geographic magazine. He's studying geometry properties of this Octet Truss. And Buckminster Fuller rediscovered it, and then my student and I rediscovered it because we were looking for a gadget for an NP completeness proof. And we thought, how are we going to design a gadget? It's so hard to visualize things in 3D. But what's rigid? Well, crystal structures, maybe we can get an idea from looking at the crystal structure of diamond. So off we go looking around, and we find this same structure that has helped other people before in the past. So this is something called the 3D logic engine, which is a device for getting NP completeness proofs in situations where you have something that's uniquely realizable. And the idea, there are many different ways you can imagine this. If you think in the plane for a bit, forget these little green dots here. These are for 3D. Just look at the picture in the plane. Forget the gray towers. If you have a combinatorial graph with these vertices and edges, and you want to realize it as a touching graph of unit disks, then you don't have any choice how you lay out a hexagon. You don't have any choice how you lay out a triangle. You don't have any choice how you lay out a hexagon. This structure around the periphery is a rigid structure. You don't have any choice about how you lay it out. And likewise, for these internal structures, you don't have any choice about how you lay them out, except that we're going to have a path that's got just the right length to reach from here to here. So it's in the combinatorial graph, a path of vertices. And that path is going to run through these particular vertices in the combinatorial graph. Now, if that's the only connection between, say, this and this, then you see we can take this part and, in our mind, rotate it. So it goes the other way. So we can start, in each one of these things, we can rotate the realization of this rigid part here. This we don't have a choice how to realize, except that we can just flip the picture over because it's got this path running through it. That's the only thing we can do. And likewise, over here, these diamond shapes, these things are rigid. We don't have any choice how we draw this subgraph, except we could flip this the other way. It's the same picture, but it's just flipped the other way. And these chains are designed to exactly be long enough to reach between the holders at the top. So we have what I call an example of a logic engine, because you can encode not all equal 3 set into this. So each one of these things that rotates around, you are going to regard as the truth-setting component of a variable. So if this side is flipped up, the variable is true. If it's flipped down, it's false. So you can independently set the truth assignments. And then these, by turning these one way or another, and deciding which ones are just diamonds and which ones are diamonds with a little extra tag on them, you can encode an instance of not all equal 3 set. So these are going to be clauses. These rows are going to be clauses. The first row above and below this horizontal line is going to be the clause 1, say, and then the second pair out is going to be clause 2. And what we're going to do for each literal is, if the literal doesn't appear in the clause, then we put a little knob here. If it does appear in the clause, then we don't put the knob. So we have to say that for the literal and for the complemented literal. So in this particular clause 1, I guess we don't have an occurrence of either x1 or x1 complement. In clause 1, we do have an appearance of x2, but not x2 complement, and so forth. So if you're going to lay this out, notice, okay, there's one other ingredient we need. These 2 points, the way they're shown there, they're unit distance apart, but in the graph we don't have an edge. So that's not an acceptable configuration. We would have to take this and flip it over the other way in our realization, and that would be okay, because there's a little gap there. So, in every row above and below the horizontal line, you have to have at least one empty space in order to get these things to be able to point toward a free position and not overlap with one another. You can't turn it this way with touch. You can't turn it this way. So you have to have a hole in there. And that means you have to have one of these diamonds without a tab. And that means the variable is in the clause. So you have to have a variable in the clause below and in the corresponding version of the clause above. So you have to have at least one true and at least one false literal in each clause. So it's encoding not all equal 3 set. And you can take that idea and put the green dots in, which means you move to 3 dimensions, and you're using the octet truss construction that I showed you. The blue is like the base construction, and the green is the triangle's lattice above that you just raise up the appropriate distance. And I won't explain what the towers and the high wire are, but the idea is make sure you get everything realized on the same side of the base plane and not some above and some below. So that's the 3D logic engine proof that shows that in 3D it's NP hard to determine whether a graph can be realized as the touching graph of unit spheres. Okay, that's it for our 2 examples of drawing graphs with geometric relationships, visibility and touching. Well, thank you very much for your attention.